Yes, let's see this case. A block of mass m1, as shown as in the figure, is fastened to a spring and a block of mass m2 as placed against it. Find the compression in the spring in the equilibrium position. This is the first part. The second part is, if the block is further pushed by a distance 2 by k times m1 plus m2 into g sine theta against the spring and released, find the position where the two blocks separate and what is the common speed of the blocks at the time of separation. Now this is basically a case which has very less to do with SHM, but basically it is a case of mechanics, in which, let's call for the first part over here, we have a system which is in equilibrium, and the system is something like this. There is a mass m1, there is another mass m2. Now the complete system is kept on a horizontal, kept on an inclined plane, such that the angle of inclination in the system is given to you as theta, and the spring is kept at one fixed end. Now basically what is there, if the system is in equilibrium, first thing is that F net would be equal to 0, and m1 plus m2 can be taken as a system. In Newton's laws of motion, we have understood one simple fact, that two bodies can be taken as a system if the acceleration of both the bodies is same. In this case, in this particular case, if I talk about both the bodies are in particularly at rest, so the acceleration of both the bodies are 0, hence bodies can be taken as a system. Now if we take it as a system and then draw the FBD, these would be the two bodies, one would be m1, one would be m2, such that if you cumulatively draw them, there would be a weights component which would be acting in the downward direction, that is m1 plus m2 into g sine theta, and there would be a weights component which would be acting in the vertical direction perpendicular to the inclined plane, that is m1 plus m2 g cos theta. There would be a normal reaction, let's call it n1 from ground, and there would be a spring force with which the first end has been pulled up, and let's call the spring force to be equal to kx naught. Now such that over here, if F net is equal to 0, then kx naught would be equal to m1 plus m2 into g sine theta, or x naught comes out to be m1 plus m2 into g into sine theta divided by k. This would be the first part's answer. Any issues up till now? I don't think so. So let's go to the second part now. In the second part, he has stated that, in the B part, he has stated over here that, let's call this to be the system, where this angle is equal to theta, and the system has been extended by a length, let's call it extra length of x naught. The system is totally compressed up till a length of let's call this to be the natural length of the spring. It has been compressed to a length of, let's call it x naught, where x naught can be stated as initial compression plus extra compression. In this part, the initial compression was equivalent to m1 plus m2 into G sine theta by K, and the extra compression given was 2 times m1 plus m2 into G into sine theta divided by K. That comes out to be 3 by K times m1 plus m2 into G into sine theta. This would have been the total initial compression in the spring. Total compression in the spring. What would happen if we leave, as we leave the system, it moves in the upward direction, such that initially they move together, but after some time they move separately. The limiting condition for which would be the time at which normal reaction becomes just equal to 0. Normal reaction just becomes equal to 0. Both the blocks separate. And if normal reaction is just equal to 0, at that state both the blocks separate, and at that point both the blocks will have same acceleration, because the normal reaction just became equal to 0. Now based on it we will solve up this particular problem. Let's call it how. See, basically when we draw the FBD of both the blocks separately, we see that if we pick up the block M1, we'll feel a force of Kx in this direction, then we'll feel a force of normal reaction in this direction, and a force of M1G in the downward direction. Now if I resolve this thing into various components, the various components can be treated as Kx as well as a normal reaction N1 in the N2 in this particular direction. We'll feel a Kx in this direction, then N in this direction, N2 in this direction, M1G cos theta in this direction, and an M1G sin theta in this direction. Such that let's assume the particle's acceleration to be a in this direction. So a can be stated as M1G sin theta plus n minus kx is equal to mass into acceleration a. This becomes the equation number 1 for the first block. And for the very same block, for the very same situation, let's consider the second block. If we consider the second block, the mass is m2, so we'll be having a force of m2 into g into sin theta in this direction, then a force of m2 into g into cos theta in this direction, then a force of n3 in the upward direction, and n in this particular direction, such that if that block had an acceleration equal to a, this block would also have the same acceleration equal to a, and hence m2g sin theta minus n can be written as m2 times a. This becomes the equation number 2. Now the limiting scenario over here is that normal reaction at this point should be equal to 0. So if you consider the second equation, m2g sin theta should come out to be equal to m2a, where m2 and m2 gets cancelled out, or a comes out to be equal to g sin theta. And if you consider the first equation over here, m1g sine theta plus normal reaction can be written as 0 minus kx can be written as m1 into a, again that can be written as g sine theta, and from this part this and this can cancel out, kx comes out to be 0. So basically it means that x comes out to be 0. So basically both the blocks lose contact when the spring is at natural length. This becomes the answer to the second part of this particular problem. That is, both the blocks leave the contact at natural length. Now let's talk about the third part. We need the velocity of both the blocks. Both velocity would be same when they just lose contact. Now at the instant when they just lose contact, we can say that they would be having a velocity. Definitely they would be having a velocity, and that can be very well found out using the conservation of energy. How? Basically the system rises by an inclined height of x naught, and the energies in this particular proportion can be conserved. Let's call this to be the change in height of center of mass, that is h. Supposedly this is x naught which he rises, and this angle would be theta, since the angle of inclined plane is theta. So the height up till which it rises is x naught sine theta. So basically if I conserve energy, u initial plus k initial can be stated as u final plus k final. Since gravitational potential energies are involved over here, I would have to take up a reference in this particular case, which is the convenient option to be taken as the initial point itself. So u initial with mg plus u initial with spring plus k initial can be stated as u final with mg plus u final with spring plus k final. Now in this particular case, u initial with mg is equal to 0, since we have taken it to be the datum. Initially the spring was compressed by a length of x naught, so I can write u initial as half k x naught square, and kinetic energy initial was taken to be 0 since the system was left at rest. Now finally the particle reaches to a height of h with respect to the datum, so final energy can be written as mgh, where m can be written as m1 plus m2 into g into h. The final potential energy of the spring can be taken as 0 since the spring came to its natural length, and the kinetic energy final which we need to find out is half m1 plus m2 into v square. So basically the equation simplifies into this particular format, that half of m1 plus m2 into v square is half k x naught square minus m1 plus m2 into g into h can be written as x naught sine theta. So basically if I simplify this particular part, half of m1 plus m2 into v square can be written as half into k into x naught square can be written as we have calculated x naught in the previous part, x naught can directly be written as (3 by k times m1 plus m2 3 by k times m1 plus m2 into g sine theta the whole square minus m1 plus m2 into g sine theta into again the factor of x naught, which can be written in the same way. If we calculate v from here, the result which we are getting in this particular case is under root of 3 times m1 plus m2 whole divided by k into a factor of g sine theta. That would be the answer to this particular problem. Thank you.